In today's video, we're going to be building the island biogeography model that Jed just talked about. You've downloaded the shell from the website, and so here's the model inputs that we'll be dealing with. The parameters are, first, the number of species that are available in the mainland pool. And you can enter a value in cell C3. So let's assume that we have 30 species that are occurring on the pool that is the mainland pool. So that's our source of species that are able to colonize our island. Now, our actual island characteristics are over here in this portion of the spreadsheet. And here we can enter the current number of species that are present. So let's enter the number 6. We'll also be able to enter more information about the island, such as its area and how far it is from this mainland population. But we're going to leave these cells blank for now. So we have 30 species on this mainland. And our goal now is to predict what's going to happen with respect to species richness on the island itself. Right now it has 6 species, and we want to know what's going to happen over time as is predicted through island biogeography theory. You might remember that Jed talked about the maximum colonization rate that he called I. And let's go ahead and enter a number here. Let's put down 6. And what this indicates is this is the maximum number of species that can colonize an empty island. So if our island had no species present, how many individual species could actually colonize the island, given that there are 30 there from the pool? So we're entering this number, and this number really is reflective of how fragile these organisms are, what is their dispersal ability, and things of that nature. So 6 is the most that we would expect under ideal conditions. So this also, if you can remember in your mind Jed's graphic, he said that this forms the rate. So here our colonization rate will be in blue, and we're looking for the number 6 up this y-axis. And so our very first point for this graph is going to be x is equal to 0 and y is equal to 6. So we'll go ahead and plot that x and y value here for our first coordinate. So in cell I3 we'll enter the number 0, and then in cell J3 we'll reference the number 6, and you'll be able to see that that plots our first point for the colonization rate. So let me just orient you to this graphic. It's the exact same graphic that Jed showed you. The number of species on the island will be represented down the horizontal axis, and the rate will be given on the vertical axis. The colonization rate is in blue, and the extinction rate will be in red. So here our colonization rate is expected to be highest when the island is totally empty and void of any species. And we now have plotted our first coordinate, which says under that condition we can expect 6 new species to arrive on our island. Now, Jed also said that this relationship, this line, will go down, and when the number of species hits 30, then the colonization rate will be 0. So we have a second point on this graph. That is, the x value would be 30, and the y value would be 0. And we'll plot that here. So our second point is x is equal to 30, and we'll reference our species pool. And I've named that particular cell pool. So if I click on cell C3, you can see that the name pool has been written, and that's why this formula says equal pool. It could also say equals C3. And if we go over 30, we're going to go up 0. That places our second point on the graph, and now we have the rate of colonization declines as the number of species that are present on the island increases. So this is all a review to this point. That handles the colonization side of things. Now we can calculate what this slope is, and we'll do that in cell C5. Now remember, the slope is calculated as rise over run. So how far down do you go with the run? So here our slope is going to be, we drop down 6 and we run over 30. So our slope is going to be calculated as cell C4 divided by the pool. And we know that this is a negative value, so we'll put a negative sign in front of this and then press OK. So you should get a slope of negative 0.2. That means that for each species we have on the island, each new species, we're going to be dropping our immigration rate by 0.2, negative 0.2 species per unit time. Now, later on, we're going to add another effect, which is a distance effect. How far is our island from this mainland? The next thing we can talk about is the extinction rate. Here, you're going to be able to enter what is the maximum number of species that could be lost in a particular time step. And again, this is one of those numbers that you are free to enter, but it would be reflective of the system that you're studying. So is it a system, an ecosystem where there's rapid extinctions? Maybe it's in a hurricane zone and there's a high probability of turnover. So this extinction is representative of the maximum number of different species that could be lost in a time step. And this now establishes a point on our extinction rate. And the maximum extinction rate will occur when our island is totally full. So that establishes another point we can add. So when our x value is 30, our y value would be 4, and that anchors the beginning of our extinction rate curve. So let's add those in here. For extinction, our first point is going to be the species pool, and our second point will be equal to cell C7. And as Jed said, the next point that anchors the red line is the 0, 0 origin. And we'll just go ahead and put 0 and 0 for that point. And now we have our extinction and colonization rates. So notice that these lines were derived from just a few inputs. How many species are on the mainland? What is the maximum immigration rate, which is determined when the number of species on the island is 0. And what is our maximum extinction rate? That's set by the maximum number of species that could be lost when the number of species on the island is full. Just like we were able to compute the slope for this colonization rate, we can also compute the slope for the extinction rate. And once again, we have that formula as the rise over the run. So the rise, we go up 4, and we've run over 30, and that should be our slope calculation. So it's going to be cell C7 divided by the pool. Now at this point, we're ready to focus on our island. Here's our island. It has an area, it has a distance. Again, we're going to ignore those factors for now. But right now we know that it has 6 species present. And we want to know what is its equilibrium number of species. So this is what we're aiming for. We're aiming to get some equations in cell F9 and then calculate the turnover rate in the next video. So in order to get to our equilibrium species, we need to move backward. And remember how Jed talked about calculating the equilibrium. Well, one of the first things we need to do is to calculate what is the immigration rate, and he called that lambda sub s, for this particular island. We know it's got 6 species present. We know there are 30 species on the mainland. We also know that we can find the number of species presently on the island, and we should be able to find what the extinction and colonization rates will be. So if all goes well, we'll find the number 6 here, and we'll find its extinction rate, and then we'll find the number 6 and we'll find the colonization rate. The extinction rate is listed as mu sub s, and the immigration rate is listed as lambda sub s. And if we know those two rates, then we can compute how many species we expect to change in each time step. So that's where we're headed. So remember that Jed wrote that formula. Y is equal to ax plus b. We're trying to compute the immigration rate. So the intercept, b, this is the immigration rate or the colonization rate, is given by the number 6. And then we need to multiply the slope, which is given by a, right here, times the number of species that are currently present. So we'll be entering this equation. So our equation, lambda sub s, is equal to, and let's just follow along, a is the slope, that's given in cell C5, times the number of species currently present, that's given in cell F3, plus the intercept, and that is given in cell C4. And I may have gotten my notation mixed up a little bit, but I hope you can just see that this is the equation of a line, and once again you have the intercept plus the slope times x, and x in our case is the number of species present, and the result is 4.8. So this means that for our island that currently has 6 species, we expect in the next time step that we'd be gaining 4.8 new species. Now how about the extinction rate? The extinction rate is the red line here, and we know that the intercept of this line, where it crosses the y-axis, is 0. So our intercept is 0, and so then all we need to do is multiply the slope times the number of species present. So that would be equal to cell C8 times cell F3. At this point, we can now compute the change in species for the time step. So delta S is the change in the number of species, S, per time step. And we can get that by just subtracting the immigration rate minus the extinction rate. And what you can see here is that our population on our island has 6 species, and it's going to be gaining 4 additional species in this next time step. We're sitting down here at 6. The extinction rate is lower than the colonization rate, and so we'll be adding new species, more species than we'll be losing, and as a result we'll be gaining new species, and in our next time step we should have 10 species on our island. Now the last calculation is going to be one that we'll just use directly from Jed's video, and that's how do you compute the equilibrium number of species. Jed derived this in his lecture, so I'm just simply going to enter it here. It's going to be equal to the maximum immigration rate minus the total number of species on the mainland. That's called pool. And then we'll divide that by the maximum immigration rate plus the maximum extinction rate. So this equilibrium number is determined strictly by these inputs here, the maximum immigration, the maximum extinction, which again are set by the ecosystem itself, and the species pool. Now I think I made a mistake here. This should be C4 times the pool divided by C4 plus C7. And we end up with our equilibrium number of species of 18. So this is exactly the example that Jed showed in his video. And let's just take a look and see where we find 18. Here we have the number of species on the island, and at 18 we see that the colonization rate is balanced perfectly. They match exactly with the extinction rate. And so at that point in time, we would expect that the island might experience different species coming in and different species going extinct, but we would expect that over time it would remain stable with 18 species present. So again, 18 species present, but from time step to time step, the composition may actually be changing. So which species are present and which species are missing may be changing with each time step. Now I've moved some of my figures around, and we're again looking at a condition in which equilibrium occurs where the colonization rate and the extinction rate lines intersect, and we end up with an equilibrium number of species of 18. One thing we can do to get a better handle on this equilibrium number is to actually simulate the dynamics of changing species numbers through time. So we set up a time series from 0 down to 20, down column A, and at time step 0 we're going to reference the number of species that are present on the island, and that's stored in cell F3. To do our time step, we need to calculate the immigration rate and the extinction rate that pertain to the time step itself. So here we have 6 species. We're going to compute its immigration rate, just like we did up here, and its extinction rate, just like we did up here, and then enter an equation that would compute the number of species that would be expected in the next time step. And we already know that answer, but let's go ahead and fill these in. So the immigration rate is computed as the intercept, which we know is stored in cell C4, and we'll anchor that, plus the slope, which is stored in cell C5, times the current number of species that are present on our island. And you can see that the formula returns 4.8, and it should match exactly this as a nice way to double check our work. The extinction rate is going to be equal to the intercept, which we already know is 0, so we won't enter that in, plus the slope, which is stored in cell C8, times the number of species present. So this is telling us how many species are we expected to lose for this particular time step. And we see that this result matches our result calculated in cell F7. Then the number of species in time step 1 is simply going to be the number that were present in time step 0, plus we'll add in those species that immigrated to the island, and we'll subtract off those species that went extinct on our island, and we end up with 10. And this is exactly what we would have predicted. So we started off with 6 species. We see the change in the number of species for the unit time was 4, gaining 4 species. 6 plus 4 is 10, and that's reflected here as well. Now we can copy these equations through, and the generating equation, and start to graph out our trajectory through time. And here the graphic displays the time step and the number of species that are on the island. So we started off with 6, and then we climbed to 18, and at that point, when we hit 18, the colonizations and extinctions are perfectly balanced, and we see that the island is now in a stable equilibrium. Now, what happens if we are above the equilibrium line? What if we have, say, 25 species present on the island? Well, in this case, with 25 species, our extinction rate is higher than our colonization rate, so we're expected to lose species with time steps. But you can see here that we drop the number of species on the island, but eventually, once again, we hit our equilibrium point of 18 species and it remains stable through time. If we look at this from the perspective of a fresh island that has no species, then we start at the 0, origin and we begin to accumulate species until we hit the equilibrium number. And this is an example of a species accumulation curve. Jed's going to be now summarizing this basic model of island biogeography, and he'll then introduce some new concepts and new twists to this idea, and that includes adding in the effect of the area of the island and its distance from this mainland species pool, and how those two factors might affect the extinction and colonization rates. So let's pass you back over to Jed, and then we'll see you again when we then continue building our spreadsheet and add in those two effects. See you next time.